Hi guys, welcome back to 100 Days Machine Learning Crash Course. Today we want to talk about regularization techniques in neural networks. So we will learn about regularization or common regularizations, dropout techniques, data augmentation, early stopping, model ensembling, and hyperparameter model selection in this session. Okay. So we actually talk about regularization a lot. Is that the difference between machine learning and optimization or plain optimization is that what we actually really care in machine learning is that the generalization error, or when we have a really good optimization technique that it could decrease the loss function really quickly, but the validation error does not decrease really well, or the accuracy does not increase as the training accuracy. So we know that we have some kind of overfitting which we don't like. Okay, so we should use regularization techniques to decrease this gap between the training and validation performance. Okay, so this is a really good graph to show the overfitting. So typically when you train your neural network, or when you are training a deep neural network, you could have this accuracy for your training data, and this graph for your validation data, which shows a little gap and little overfitting, which is really okay. So, and this is actually a good model in here. But sometimes you have this performance for your training data, but this performance for your validation data. So it really could show you the overfitting, or a strong overfitting for your validation data. What should you do in these cases? Okay, so the first thing that we learned in traditional machine learning methods is that using L2 regularization or L1 regularization or elastic net, which we didn't talk about that, but it is actually a combination of L1 and L2 to add it in the cost function of neural network. So when we use the L2 regularization, we just add this term in as the regularization with a hyperparameter lambda, and we set the lambda, and then we are forcing the network to having small weights, because if the network has large weights, then this cost function will increase, because we have a term of w square in here, okay, in this term. So it could actually makes your network to have small weights. When you have small weights, let's say this is space of the weights. When you have small weights, in other words, you don't have really large weights, you are in this region, or your model or your hypothesis space is practically this space. So in fact, with regularization, you are reducing the variance of your model. Okay, I hope you understand this. Maybe it is a little confusing, but it is what it is. So in other words, instead of having infinite possibilities for choosing W1 and W2, which is a model with high variance, or a high variance space, you are limiting the variance of the space by adding this term, and prefer these models over these models, and you are reducing the variance of your model. So this is the idea behind all the regularization techniques, whether it is L2 regularization, L1 regularization, dropout technique, or any other regularization technique that we will see. Okay. So we have seen that we have some kind of bias variance trade-off for the models. So when you have a very simple models like linear models, you have low variance because practically you are just confining yourself to the linear models, but so that is good, but you have high bias, or the training error is high. You are misclassifying all of this data. Okay. In contrast, when you have a really complex model, a very high nonlinear model, maybe a deep neural network or a neural network with lots of neurons, then you probably have high variance. In other words, your hypothesis space, or the functions that you could show, you could create with that models is a lot. So you have high variance, but a very low bias. In other words, you have zero training error in here. Okay, but probably a bad generalization for your network, or in other words, high variance. Okay, so between those you have a good sitting point, which is a low variance and low bias. It is actually relatively low variance and low bias. Okay, so you don't have zero training error. It is some training error, but it is not that much. It is not that much. Also, you have some kind of variance that is right for your kind of data. It is not really a lot for your data, or really low for your data. Okay, so we are looking for this kind of, to make this high variance model these models. Okay, because when you have a deep neural network, it could have a really high variance. But with some techniques, for example with L2 regularization, we are reducing the variance. So we are moving toward these kind of models. Although the plain deep learning neural networks or deep neural networks have very high variance. Okay. So okay, about this is a point about L2 regularization. It's called actual weight decay, because when you use this lambda r of w and you choose the w to be the second norm, you could write the second norm as w transpose w, because if w1, w2 is your weight vector, the w1, w2, w1, w2, which is this dot product, gives you the second norm of your vector, of your weight vector. Okay, so you could write the second norm as w transpose w, and when you want to use gradient descent, you should calculate this, right? So you have a term to calculate the gradient of this, and you have another term which is the gradient or the derivative of this term. Okay, so and you could actually calculate that explicitly based on w, okay, in terms of w. So you could see that now the W will be W, which is the initial weight, minus 2 lambda, which is the lambda is the regularization parameter, times W. Okay, in other words, you are decaying or reducing or decreasing the weights. Okay, for this we call it a weight decay regularization. So either it's called L2 regularization or weight decay. And so regularization can prevent overfitting and for example, L2 regularization, because creates a small w that we talked about it. So when you have small weights, you are probably in the linear regime of tangent hyperbolic, and you are not in this regime that could be good for you to train your network. Okay, the next technique to regularize the network is dropout technique. So let's say we have this neural network. Instead of having this complex neural network, we could drop some of the neurons randomly and train the network. Okay, so with a probability, for example, 0.5 or any other probability, you drop some neurons and train your network. So in this case, you are training a smaller network for each sample. Okay, and this could actually have the regularization effect. Let's see why. When you are removing or dropping these connections randomly, then you are preventing the network to put really large weights on one of these links. Because if the network put large weight on, let's say, this link, then it means that the output of this neuron governs by this input. But if you removed that link randomly, as dropout works, then the output will change. Okay, so and the network will see that, wow, I have a change in my input, in my output, which is not the ground truth. So it learns that it should not have it should not rely on just one input. So it tried to have not large weights on each links. So the dropout could act like L2 regularization and weight decay in the sense of it does not allow the weights to be really large. And another intuition about dropout, which is good, is that it does not allow two neurons to be really high correlated. Okay, as I mentioned, because it does not allow two neurons to have really large weights between them, we could say that an output of neuron is created by looking at all of the previous features. Okay, so let's say the first neuron in here are specifying that the input, which is probably an image, has an ear or not. The second is that has a tail or not, and so on. So if we don't use dropout, probably maybe when your network learns how to learns when it see an image has a tail, then it will says that it is a cat, and the cat score will be large. Okay, So it means that it put 100,000 or 1,000 on the weight of between these two neurons. But when you use dropout, then it try to use all of these features to share some information to create the output, which is really good. So now the network look at all of these features and create the output. Okay. So to create simpler models and use dropout, we have lots of different possibilities for the network, because each weight could exist or be dropped. So what should we do in these cases? The thing is that dropouts makes our output random, because we say that some of the links or some of the weights could be dropped at the training time. So the output will be a function. So this is the function of neural network. So it will be the function of input and a random mask. A random mask is actually, let's say we have these weights, W1, W2, and the output. So we could say that the output is this, and to include the dropout, we could think that we have a mask, a binary mask, which is either 0 or 1. If it is 0, it means that we are dropping one of these, right? Or if it is 1, it means that they are existing in the network. And when in the test time, we should average out for the randomness. So we should get the expected value on the Z, or with regard to the Z, to get the output. Okay. To calculate this integral or this integration, we could use the discrete form of this integration, right? So at test time, all of these weights are existed, right? At test time, we don't remove any weight. So the output is W1x1 plus W2y as the output, okay? The expected, we don't have any kind of randomness in here. But during the training time, we have 4 different states. In one state, with similar probabilities, with equal probabilities, maybe we drop this this weight, which is create this term in here. We could drop this one, which is create this term. We could drop both of these, which create this term, and we could drop none of these, which create this term. So if we calculate the expected value of A, will be 1 over 2 of W1x1, W1x plus W2y. So as you could see, we have 1 over 2 factor in here, but we don't have any factor in here. Okay? And so we should multiply the output at the test time by the dropout probability. Okay? And we have some notes about the dropout, how to use them in the test time, but because we use the frameworks that we use, for example, TensorFlow or Keras handles them automatically. We don't need to go into all of the details. Okay. So the dropout could prevent overfitting a lot, and you could use the dropout technique for your neural network. But when you use the dropout, your cost function is no longer well defined because you're randomly dropping some of the neurons. As a generalization of regularization, this is a very common thing in regularization. You write your output based on some randomness, and in the test time you average out that randomness, okay, to get the output. This is a common pattern in regularization. Okay, so we will see that in fact dropout could act like the ensemble model of simpler models in deep neural networks. Or in other words, we could think that the dropout, when you use dropout, in fact, you could think that you have simpler models instead of one complex model, and it is kind of model ensembling. That is actually cool about dropout. Okay, so let's back to this common pattern. We will see that a pattern could be batch normalization, could be right like this. Okay, so we normalize the inputs based on the statistics of random mini batches. The next thing is that we want to talk is data augmentation. Okay, many of the times maybe you have a limited number of training data, or your training data set is not so large, so but you need more data to train your neural network. In this case, you could use data augmentation. So if you have, let's say you have this image in your training data set, then to train your network, you could have this one, and also you could horizontally flip your data set image to obtain this one. So now if you have 1000 images, you could create 2000 images to train your neural network. Okay, so that is cool, and it is one way to augment your data. Another way to augment your data is random cropping. Okay, so if you want to recognize cats, maybe you want to crop this part and scale that to the standard size of your neural network and pass this to your neural network. So you could have random cropping from your image to train your network. Okay, and also you could have some contrast and brightness change in your input to augment your input. Okay, or color jittering. The most common thing is that maybe translation which means that you want to shift your image left, right, or up and down. You could have rotation, stretching, and sharing. And also you could have a combination of those. We will see that when we use Keras. Actually, Keras has an option to use the data augmentation in the training. Okay, so you could use the data augmentation online for your training data. Okay, so we will talk now about this dropout. Actually, we talked about it, but to see this as ensembling of simpler models. I hope that now you have gained this intuition about the dropout, which is some kind of adding randomness to your network, and at the test time you marginalize over that randomness. Okay, in this case the randomness is removing the weights. Okay, we could have other kind of randomness. For example, we could add random noise to the training data and marginalize over the noise in the test time. Okay, and actually there are other things that we could use. Maybe these are not really common in regularizing the neural network. Okay, so another thing that is really important in training is early stopping. So similar to L2 regularization, in fact, let's say we are training our neural network and you are decreasing the cost function by the gradient descent. Let's say you are using Adam or Arms prop, and you just need to stop at one point. To do this, you could track the validation accuracy or validation performance or validation loss, and when the validation loss starts to increasing, let's say in this point, you stop your training. We call this early stopping. So you're monitoring the validation performance or validation cost, and then stop the training or early stop the training process when the validation cost starts to increasing. And it could act like L2 regularization because it does not allow you go in here. Here is the region of high bias, and when you have high bias, you could have large weights in your neural network. If you remember that if you had some kind of these points, this is a high bias model. Okay, and it has large weights. So if you stop the training process or training procedure in here, it means that you don't allow the weights to be really large. It could act like L2 regularization. Okay, now we want to talk about model ensembling, or the first way is to train multiple models and average their results at the test time. Okay, so we have seen that dropout could act like an ensembling of models and averaging at the test time. Okay, so we could have also different options to use model ensembling. For example, we could use same architecture of neural networks, but with different initialization. So for example, for one of them, you could use a Gaussian initialization. For one of them, you could use Xavier initialization, and so on, and train all of these. And after training, you get the average over all of the output of these neural networks, okay, to ensemble all of this model. So this is one way. Another way maybe is the best models discovered during cross-validation. So we are probably training your different neural networks with different hyperparameters. Then you select the top models with top performances to use for model ensembling, or also you could use different checkpoints of a single model if the training is very expensive. So if your neural network is really large, then you probably cannot train lots of different models. So you could just train one model. So for training, when you are training your model, you could save your model weights in different points. Then during the test time, you average out over all of these, all of your model. It is just one model, but because you save the weights in different points, so it could act like an ensemble of models. Or you could run an average during the training. So instead of changing all of the weights, you could run a moving average, like parameters for the parameter of your network. Okay, so in this case, you could see having checkpoint for your neural network and using ensembling. So we are using some kind of snapshots in different points to train in the training procedure, and at the test time we are using all of these information to get the output. Okay, another way is using cycle learning rate schedule. In other words, you are when you are in here, let's say we are in here, then by reducing the learning rate, we are going to one minimum, then we increase the learning rate, so we are oscillating a lot probably, so we will go to here again, we reduce the learning rate, so we are going to the next local minimum, and so on. So in this case, we are getting lots of checkpoints to do the ensembling. Okay, and also this is related to the moving average of the parameter vectors that we talked about it. So the hyperparameters that you could choose to have better convergence is the learning rate, which is a really important hyperparameter of your model. The second thing is that the regularization strength, so it could be the dropout probability, it could be the L2 regularization factor, which was lambda, and so on. It could be the number of hidden units, or the number of your layers in the neural network, or the mini-batch size, okay, or your decay schedule for your learning rate. And also the parameters of the optimization algorithms like beta 1, beta 2, and epsilon. But usually the most important ones are actually these ones. Okay. So the question is how to optimize those hyperparameters. So the first thing that we could use is cross-validation strategy. Okay. So we use the cross-validation method to get different performance on different models with hyperparameters, with different hyperparameters. Then we select the best model. Okay, so and the search that you should use is a cares to find search. Why? Because let's say you have a neural network with different hyperparameters. So if you want to train 100 neural networks with different hyperparameters, which is not really a lot, but let's say each of them takes 1 day to fully train on your data, then for 100 neural networks you should wait 100 days, which is insane. Okay, so to find the good hyperparameters, first you don't need to fully train your model. So instead of training your model for 1000 epochs, maybe you train your model for only 5 epochs to just get the rough idea of what kind of parameters are working well. So this will be the first stage, and after that you could find your search in hyperparameters and having longer training, for example 10 epochs or 20 epochs, to find the best hyperparameter. Okay, and for having random hyperparameters, use the log space. So if you want to test different regularization, let's say L2 regularization factor, then don't use this kind of search. Use the log space. Okay, so you probably have these factors for your searching. First you should do that carefully, so you have a very large range. Then you could find your research and your search hyperparameter region to get the best parameters. Okay, or in other words, you are adjusting the range. And probably when you are training, when you want to use the hyperparameter optimization, you don't have lots of resources to do that. So if you have 10 different parameters for your learning rate, 10 different numbers for your maybe number of hidden units, 10 different numbers for minibyte size, then you will end up with 1000 experiments that you should train your model, which is a lot. Okay, so one of the ways to mitigate this problem is that using a randomly sample from this 1000 samples. Okay, so in this case we have grid layout. We call this grid layout, but we could use the random sampling from this parameter space to search for hyperparameters. And it is actually more effectively and more easily to do so. Just use the random search to optimize your hyperparameters. Okay, so the last thing which we want to talk about it is babysitting one model with training models in parallel. So instead of having, we have two different strategies to create a good model. Okay, so the first thing could be we train different models with different parameters and select the best model at end. We call this KVR approach for selecting hyperparameters. I think it should be A in here. We are training many models in parallel to and select the best hyperparameter. The second approach is that it's called babysitting one model called Panda. In other words, we are just training one model and fine-tune the hyperparameters for that model to get the best performance for that model, especially when we have just limited resources. So when we have limited resources, then we could not run lots of training of models in parallel. So instead of that, we just use training one model, but we use different kind of adjustments for this network for getting the best performance on our network. For example, we could use learning rate schedule or shrinking the batch size or other stuff that we could use to having the best performance on with just one model. So it is in comparison with this method. So if you have lots of resources, you could use the KVR approach. But if you don't have lots of resources, you could use Panda method. Okay, hope you enjoy from this session and learn about regularization techniques and some other things into deep learning, and hope to see you in the next session. Bye.